I'm going to continue the chapter 2, which is the easiest one, I believe, talking about the forces acting on particles. Last time we split the entire chapter into two parts. One is the two-dimensional problems. The other one is a three-dimensional problem. I was pretty much done with the two-dimensional problem. So today I want to just quickly go over two-dimensional problem before touching down the three-dimensional problems. Okay? For two-dimensional problems, there's the first part here. So we basically talk about two things. Number one, how to calculate the resultant or the resultant force if we see a lot of 10, 3, or 100 forces acting on that certain particle, right? So that's the first part, is to let us calculate the resultant force if we see, for example, 4 forces acting on that point, right? So these are the real 4 forces with the directions, with the magnitudes. But we don't want to deal with those 4 forces. We got too many forces, right? You don't want to count one by one. Instead, you want to create an equivalent one force which can replace the total contribution of these 4 forces. And that is called the resultant force. And your job is to calculate that resultant force in terms of the magnitude and also in terms of the directions. Okay, so these are the two things to represent a vector of force. So basically, when we have 4 forces, we just need to calculate the resultant force. The resultant force is not real force, by the way. It's a virtual one, but it's equivalent to those 4. Or you have 100 forces acting on this particle, then the resultant force is a virtual one, but is equivalent to that 100 force total contribution. You have a question? Okay. Any other questions? Okay, so that's the first thing I talked about last time, right? And then the second part in this two-dimensional category is to calculate something further if we see all the forces acting on this particle and then that point is under equilibrium. If that's the case, then what? From Newton's first law, the resultant force, that's a total one, is equal to 0. So if this point is under equilibrium, that's a Newton's first law. So then correspondingly, we have 2 equations for us to calculate 2 unknowns. Okay, so that's the fundamental equilibrium equation or equations to solve for 2 unknowns. Okay, so this is still the first part. The second part is we talk about equilibrium of a particle, and I gave you another 2 examples. But before we talk about, these are the 2 equations, right? Before we talk about those 2 examples, which I did yesterday, you need to understand a concept which is called a free body diagram. Okay, so all these equations, these 2 equations, must be applied based on the equilibrium, based on the free body diagram. So in other words, normally we see these kind of pictures. Normally, when I give you a question or give you an example, I only show you this. This is the real scenario. Okay? It is your job to plot or to draw the free body diagram. And many times it is very straightforward, in fact. Okay? Because especially in this chapter, how to plot or how to draw a free body diagram, all you need to do, number one, is to find out that particle, having all the connection to that particle, only one point. And then number 2, you put all those equivalent forces on that particle. And then you're going to calculate all the components, add them together, and set them equal 0. Okay? That's why yesterday I was giving you two examples. This is the first example. You see, this is a real scenario. People trying to unload a car from the ship to the ground. Okay? So this the way they design. It's our job to calculate how much force needed from this person. And also correspondingly, if we want, we can calculate the force given by the crane. Okay? So this is now the free body diagram. It is our job to plot the free body diagram based on this. So then, first off, we need to find this point because this is a common point connecting all the sources. And then we plot something like this, which is called the free body diagram. Once we have this, then the 2 governing equations are derived or are developed based on this one. So the 2 equations for two-dimensional problem are not developed based on this. Because this one, this original picture, you don't see the real forces there. But if you see this one, which is called the free body diagram, you see all the forces. Okay? The other example I was telling you yesterday is last time is this one. So we have a river with the small boat with an engine. So there's 3 cables connected to this point. It's in equilibrium. In other words, a constant speed toward that direction, straight line. And how are we going to calculate some? We need to calculate 2 things: the drag force exerted from this boat, and also another tension or the magnitude from this cable AC. So the same thing. It doesn't matter how many cables connected to the point. All you need to do, number 1, plot the free body diagram. This is the real scenario, but this is not called a free body diagram, right? So you need to, based on this, to plot the free body diagram at this point. After you get this free body diagram, and you find out there are totally 4 forces, for example, like this, you just need to calculate each the components of each force, one by one. If you want to create a chart, no problem. You want to follow this one with more vector form, that's also no problem. And then you add all the x components of those 4 forces together, and the set equals 0. That's the first equation we have, which is right here. And then the second equation you can get is to collect all the y components of those 4 forces and add them together, and set equals 0. And that's the second equation. So from those 2 equations, you can see there are 2 unknowns, right? That's a perfect, it's a complete equation system. From those 2 equations, they are linear algebra equations. Obviously, you can calculate those forces. Okay, so these are the 2 examples I mentioned last time. And by now, you should be able to calculate pretty much the 2-dimensional problems with forces acting on a certain particle. Okay, including the very previous picture I showed you at the beginning. Let me go back to look at that picture, this one. So now you can think about it. If we know this person's self-weight, for example, okay, then can we calculate these 2 cable forces if we know the geometry? That's very straightforward, in fact, okay? Just think about it. We have more complex questions than this. This is very simple, in fact, okay? If you still do not know it, you can feel free to ask me later on. Okay, so now we are moving on to 3-dimensional problems. So if you go back to look at the 2-dimensional problems, we are pretty much calculate those components based on some kind of common sense. So we didn't follow a very systematic mathematical way to calculate the 2 components. So that's why if you go back to look at one of these questions, one of these examples having a 1 force, for example, this one, right? So if there's a force acting on point A going down, then obviously I just tell you the x component equal to 0 and the y component equal to -60, period. Okay? Because I know it, because I know the direction. I set up this is the x direction, this is y direction. Obviously, I can easily know this. I don't need to use formula. But you would say, well, how about more general, like this? So if I have a force acting on the point A going to this direction, all I need to know is to know an angle, right? So once I know this angle, I use this one. I don't know what's the magnitude for this, 40, right? So this magnitude is 40 times the sine of this angle. So 40 times sine of this angle, and I get a number. And then I put additional negative sign because I know it's to the left. So these are my common sense to calculate components of forces. I don't have a unified formula to calculate component, in fact. If I really want, I can do that. But I don't need, because that's 2-dimensional in general. That's very easy to figure out. So what is the y component of this force? Of course, I need to calculate having this one, which is 40 again, times cosine of this angle, right? And you get this one, and this going up, and then you just put a positive sign. So these are my common sense. I can easily figure out, which means you could be easily figure out how to deal with that. So that's why I don't give you the formulation. However, when we deal with the 3-dimensional problems, it's not that simple. If that's the case, we need to 100% rely on mathematics. So now I'm introducing 3-dimensional problems, and I'm hoping you need to use more mathematical way to deal with the forces in 3-dimensional setting. So normally, when I give you a force acting at point O or particle O, so if in 3-dimensional setting Cartesian coordinate system, normally we say this is x direction, for example, this is y direction, and the z direction, you need to make sure it's follow the right-hand rule. Okay, so when we have x direction and y direction, this z direction must be going to this. It's not going to the other way, because if going to the other way, it does not satisfy the right-hand rule. So in typical mathematics or statics we're talking about, we always want to make sure the three-dimensional Cartesian coordinate system satisfying the right-hand rule. So basically you use your right hand, you rotate from x to y, and then this thumb direction is a z direction, is a positive z direction. That is something always need to check first. Okay, of course, with those given examples, we're always following that. Okay, so now when we have a force vector acting on point O, how are we going to calculate the three components this time? Right? Because the three-dimensional problem, we need to calculate three components. Okay, so there are two ways we can do. So I'm going to talk about both. The first one is to look at the angles given. And if we are given with a certain angles, then we can calculate the three components based on enough angles we got. So normally we need to have two angles, and such angles are called Eulerian angles. But it doesn't matter whether you know that or not, because basically as long as you know these angles specified in the certain picture, then we should be able to calculate the three components in three-dimensional setting. So that's the first way normally we calculate the three components. There's another way which is more systematic, and almost all problems or examples, maybe 90% of questions, are using the second way, because the second way is more systematic and it's very easy in fact. So you don't need to worry about too much from your own brain to figure out the picture. You don't need. All you need to do is to follow the mathematics, which I'm going to talk about as well. But before I do that, let me go over this first, the first way to calculate the three components. So again, if there's a force acting on point O, going to a certain direction, the magnitude of this force is F, for example, italic without arrow on top. Okay, so then we need to figure out what are the angles, right? One angle is the angle between y direction and the force direction. It's called the theta y. And the other angle given is called the phi, which is the angle between x direction and the projection of this force F in this xz plane. This is called the projection, right? So that's another angle. Okay? So from this picture, first of all, we can calculate the y components very easily. Is simply because now we know this angle theta y. Look at this picture. If we know the theta y, then we can easily build this triangle OAB. So this AB is perpendicular to this y. Although you say, well, this is not 90 degrees. Well, this is three-dimensional setting. In fact, it is 90 degrees. You just look at it from a certain angle, right? So if this is 90 degrees, then this magnitude F multiply cosine of this theta y. Cosine, they gave you this, right? So F times cosine theta y, you get this y component. And that is the y component of that force. So basically we are writing like this. So the y components of this y, of this force equal to F times cosine theta y. First of all, we got a y component because of this angle we already know. And then we need to calculate the x components and the z components of this force. Because we didn't know the angle between this F and then z axis is not given. So this theta z not given. Then we just cannot find the z component directly. And we don't know the angle between this F and this x components, x direction. Then we cannot calculate the x component directly. But that's fine. Through this projection, with this force acting from O to A, we can first calculate the projection of this force on this xz plane. Okay? So the projection, we just give a name. You can give any name you like. Let's say we call it FH. That's a projection for this force on this plane. Okay? So assuming you have an X-ray or a sun-side parallel shooting in that direction, then this is a projection. So this projection is this, or this. So obviously this time we need to have a F times sine of this angle, which is this one. But this is this because it's a parallelogram, right? So the projection, you can give any name you like, FH equal to F, which is the magnitude of the force, multiply sine theta y to give you this projection. So once we know this projection, we are looking at this xz plane only. Because this should be the x component of the force. This should be the z component of the force. Now we have this projection called FH. Now from beginning, we have the angle phi here. That's the angle between OX and FH. So then FH multiply cosine of this angle. That should be the x component. So x component of the force equal to FH. This is the magnitude. Multiply cosine phi. And that should be the x component. Correspondingly, what is the z component? Or this one. So this one, the same with this, again from this triangle with a 90 degree here. So then FH times sine phi, that should be the z component, which is right here. So FZ, z component, equal to FH multiply sine phi. And FH is obtained from here. So you plug in this one in these two equations. These are the final answers for x components, y components, and the z components, right? Okay, so this time we are still kind of relying on the picture, but that should be very straightforward in a systematic way. So this is the one way to calculate the three components if we know a force with a certain angles. There's another way which I'm going to introduce. Okay, but before I introduce, let's make it very general. Okay, so assuming this time we have a force acting on point O again, the force is called F with a magnitude F. This time, let's say we have Fx, we have a theta x, which is the angle between F and the x direction, or we know theta y, which is the angle between y and the force F, or theta z, which is the angle between this force and z direction. So if we know these three angles, in fact, that's very easy to calculate those components. Okay, so correspondingly, Fx, this time, if we know the theta x, then obviously that's F equal to F times cosine theta x. Because if you look at this triangle, right? If you look at this triangle, okay, and this is the right angle, you may say, wow, this doesn't look like a right angle because there's three-dimensional drawing. Okay, so this one, in fact, is perpendicular to this. Then this component is called Fx, should be equal to F times cosine of this one. You may say, wow, this look like this is longer than this. In fact, now, if you don't believe it, you go back to look at, you replot. In fact, this one is longer than this. Okay, but the bottom line is, if we know the theta x, we can easily calculate Fx. Or if we know theta y, we can easily calculate Fy. Or if we know theta z, we can easily calculate Fz, which are the component corresponding to the three axes, right? Okay, in fact, these three angles are called direction, the cosine of these three angles, cosine theta x, cosine theta y, cosine theta z, are called direction cosine for F. In fact, later on, when you need to identify or characterize the force direction in three-dimensional setting, how are you going to characterize the directions? And normally, this is the only way to characterize the direction of a force in three-dimensional setting. Because two-dimensional, that's easy. If you go back to look at two-dimensional forces, right? So all we need to do is to calculate one angle. That's it. But for three-dimensional, it's not that easy. So instead of talking about angles, we basically calculate the three direction cosines to represent the direction of the force in three-dimensional setting. So if finally you are asked to calculate a force in three-dimensional setting, you need to first give them the magnitude of the force. In addition, you need to give the three direction cosines of that force to indicate the direction. Okay, so back to here. So I just want to define, these are called the direction cosines, you should be familiar with. Okay, so once we got these three components, then the total force, that's force, F, already one, can be written in terms of the three components, but in vector form, right? So we defined a long time ago. So the unit vector of x is called I, the unit vector, and the unit vector of y direction is called j, and the unit vector for z direction is called k. So these are the three unit vectors corresponding to the three axes. They are vectors. But you have this vector, unit vector, multiplied with the components. That means is the x component in terms of the vector in that x direction. Correspondingly, this all total is the y component vector, and this is a z component vector. You add them together, that should be the force in three-dimensional description. And you plug in those three equations into this one, every term has F. That's a magnitude. You put it out. So then what's left? Cosine theta x times I cosine theta y times j plus cosine theta z times k. These all together, we gave a new name, which is called lambda. This lambda, in fact, is the most critical vector to represent the force direction. Because once we define these three together called lambda, then this f is still here. This all total is lambda, but it's vector. Finally, you end up with what? You finally end up with the force vector equal to force magnitude multiplied with a lambda. You may say, that's not a big deal. I can easily see how the derivation process works. But the physics from this equation is very significant. The reason is, originally you are talking about a force vector, right, in physics. So that force vector is a physical concept. It's called a force. Of course, that's a physical quantity. And it's a vector, because that's a direction. That's three-dimensional physics. Through this expression, if you look at the right-hand side, there are two terms on the right-hand side to describe this three-dimensional force vector, which is the physics, right? The first one is called the magnitude of that force. That's much easier than the force vector, because we only have a magnitude. Magnitude means what? It's a number, 100 pounds or 100 Newton. That's it. We don't need to worry about the direction. Multiply with another parameter or term, which is called lambda. In fact, lambda is called the unit vector of force direction. So this lambda is a unit vector of that force direction. It's a very simple equation, but it indicates a lot of new things if you look at it very carefully. Again, left-hand side is 100% physics. The right-hand side is a 50% physics and a 50% math. Because the first one, F, is a physics, because that's magnitude, right? In math, we don't talk about magnitude. We talk about magnitude in physics or engineering, because that's the magnitude of the force, for example, right? But the second term called the lambda, they call the unit vector of that direction. The direction is a mathematical concept. A unit vector, of course, is a mathematical concept as well. So now you are having a total physical force concept, which can be split into half physics, half math. And it's very easy to deal with the right-hand side, because we can easily find out the magnitude. And it's not that difficult to find out the direction, because we can use mathematics, 100% mathematics, to determine the second term on the right-hand side. And of course, how to calculate the unit vector of that force direction. You say, well, by definition, this is the definition. Well, if you use the definition, you never calculate, because we don't give you the angle. So instead, we can find an easy way to calculate this unit vector, as long as we know 2 points on that direction. And that is the formulation now. Okay? So let's say we have a force acting a general point or a particle. It's called M. It can be 0.0. It cannot be, it doesn't matter, any point. So if there is a force F acting on point M and through a certain direction, right? So this force from the previous equation, that should be equal to the magnitude of this force. So this F right-hand side is different from the left-hand side, because this one is called the magnitude. In other words, I don't have the arrow on top. This one, I have an arrow on top of this F. So they are different. So this vector force equal to the magnitude of the force. Let's say we assume we know that is 100 pounds or 100 Newton, whatever, okay? Multiply with a lambda. Lambda is a unit vector for that direction. So now the point becomes how to calculate this lambda. The bottom line is, as long as I know 2 points, 2 arbitrary points in that line. So let's say we know point M, we know point N. Of course, normally when you look at the certain examples, you need to identify 2 points. It's really up to you, right? So point M, point N. If we know these 2 points with 3 components, point M, 3 components, x1, y1, z1, and this point N, x2, y2, z2, then we can basically calculate lambda. How to calculate lambda? First of all, we're trying to find out the distance from M to N. So from M to N, that has nothing to do with the force. Okay, we already identified 2 points, then we just use those 2 points. So there's a vector D joining M to N, from M to N. Then basically you have the x components of this distance, which is called dx. That means x2 subtract x1. So dx is x2, subtract x1. That should be the x components of this distance vector. And I call dx times I, that's still in the x direction, plus the y components, the distance vector from m to n, that's going to be y2 subtract y1. So y2 subtract y1, you get dy. Similarly, you get dz, that's a z2 subtract z1. So we got these three components, distant components, we put them together, that's called distance vector. But this distance vector is not unit vector, it's not unit vector. So in order to get as a unit vector, you need to divide it by the norm, or you need to divide it by the real distance from m to n. So that's why originally you have the vector, distance vector from m to n, which is right here, but you need to divide it by the distance from m to n, or you call the norm from m to n. How to get the distance? That's very easy. You basically have dx squared plus dy squared plus dz squared and then square root. And that's the distance formula, right, in three-dimensional geometry. Okay, so I did not write this d, I just forgot. So d equal to square root dx squared plus dy squared and the dz squared. Okay, so through this process, we finally identify lambda, which is called the unit vector. So again, the conclusion is, all we need to know is to find out 2 points in that force line direction. As long as we find 2 points, it can be any arbitrary point, it doesn't really matter. This point F does not need to be the original point the force applied, it does not need to be. Of course, you find that point, nothing wrong. But just in case you find other 2 points, as long as it's in this force line, that's enough. So with those 2 points, you can calculate lambda, which is called unit vector. So once you get this lambda, you plug it back here, then you can claim you can calculate the 3 components of f. That is fx equal to the magnitude times dx over d. That's exactly this first term. You're plugging back there. And then dy divided by d times the magnitude of the force. That's y components. And z components is dz divided by d times f. So through this process, you see, we didn't use any angle at all. Right? So again, all we need to know is to find those 2 points in that force direction. So once we can identify those 2 points, any arbitrary 2 points, then you use this equation to calculate the 3 components of the force. And actually, you know what? After you got those 3 components of the force, you can go back to calculate the direction cosines even if you want. Because these 3 components are directly related with this or this. You can calculate theta x, you can calculate theta y, you can calculate theta z. So again, in order to calculate the 3 components of the force, which basically use this equation, do not seek help from this equation, because normally we do not give you these theta x, theta y, theta z. Instead, all you need to do is to find out 2 points from that force line direction. Okay, so that is kind of simple theory in 3-dimensional force calculation. So then what I'm going to do is to show you some examples. Just basically use these equations, right, to calculate.